Okay, here is the second of the AS mock exams, and this was Physics PHYA2, so it's the second module, and it's also very close to the summer 14 Unit 2 paper. Pretty much identical, give or take a few questions. Okay, once again I'm going to do this one cold so I can see what sort of mistakes I would make and therefore which bits would catch us all out. Okay, so we're starting with a very simple graph. It's a velocity or a speed time graph, and describe the motion of each car. Well, A, that's a bit tricky to see actually, but A is of course going across there. It's constant speed, so A is at constant speed. 3 marks. What about B? Well, a straight line implies acceleration, then constant speed, so it accelerates. And let's put some values in from 0 to 5 seconds, then constant speed. Okay, so what looks to be straightforward, but give it a little bit more finesse, give it some values. Okay, what about the distance travelled by each car in the first 5 seconds? Well, the distance travelled on a velocity time graph is the area under the graph. So 5 seconds relates to that point there. So for car A, which is flat line, it's simple. You're just looking for the area underneath. So the area would be, we have 16 meters per second and we have 5 seconds. So this area is very simply, the distance is going to be the velocity times the time, or the area 16 times 5, which should give us 80, 75, 530, 80 meters. Okay, what about B? Well, with B, we have these 2 points. We've got a triangle and a rectangle. It's 14 there, 18 at the top, 5 seconds along the bottom. So let's work out the triangle to start with. The triangle is going to be a half times the height by the base. Base times the height, which is 18 minus 14. This gives us 4, 20 gives us 10 meters. Then, of course, we want 14 times 5, because that will be the area of the triangle. 14 times 5 gives us 70 meters. So you add those two together and it gives you 80 meters. So 80 meters and 80 meters. Yeah, straightforward, I hope. Nothing different there to Year 10 work. Good. At time t equals 0, the two cars are level. Explain why car A is at a maximum distance from B ahead of. Okay, so it's talking about this point here. Why is it that it is maximum there? Well, what do we have? I would say that we're heading the same speed. So at the point, at 2.5 seconds, cars moving same speed. So therefore, before then, A is moving away from B, or should we say B? Sorry, A is moving away from B. B's having to do the catching up. After 2.5 seconds, B is catching up. So therefore, the greatest distance will be at that point, because A has been travelling faster than B for the entire time. So therefore, why is A at a maximum distance away from B? Because before 2.5, A has been moving faster than B can. So it's constantly grown in its distance. So those are the 3 points you'll be given there. Okay, so far so good. They like to give you a slow warm-up to these questions. Let's look at the second question. You have a long jumper. They're talking about your centre of mass moving. Calculate time positions A and B, and this is the midpoint between the jump. So that's a maximum height. Calculate the time between position A and B. Okay, so if you've gone, let's say if you've jumped, normal parabolic motion means that at your highest point to your lowest point is going to be maximum height to 0 vertically. So we say S is ut plus a half at squared. And we can say that initially this vertical speed is at 0 because they're at a maximum height. They're halfway through their flight. So we can say that's 0. So S is going to be a half gt squared. T, of course, is going to be 2s over g square rooted. Just want to reiterate that point there. If you're at the midpoint of your jump, you're at a maximum height, and vertically, and we're dealing with vertical speeds there, vertical accelerations there, which is g, vertically this is not moving up and down at all. It's actually, though it's moving horizontally, vertically it's not moving. So therefore we can assume this relationship. So 2 times 1.2 divided by 9.81 all square rooted gives us a value of 0.4946. How many significant figures? 2 there. 3 of g, but it's the least, 2, so we're looking for 0.49. In actual, so 1 for taking that equation, substituting answer. 0.5 would have been okay, they would have given me a mark there, but definitely not 0.50. That's incorrect, because that does not imply rounding. It's quite an important point there, actually. So don't just put an extra 0 on to make it look neat. If it's that number, 2 significant figures, your answer is 49, not 5. Okay, now we are... Okay, now they're moving horizontally at point A at 8.5 meters per second. So therefore, how far do they move? Well, the distance horizontally is going to be the speed horizontally multiplied the time period. So we have 8.5 multiplied 0.49, giving us 4.2 meters. Very straightforward. The time taken for the athlete to stop, assuming it's on. Okay, so now I'd like to picture it like this. We have a velocity time because it says the resistive force is constant. So I read that to say that F over m, which equals A. If the resistive force is constant, the acceleration is constant. What does the acceleration look like? Well, you've started from a point and you're finishing. And it's asked you to work out the time taken to stop. And you know this is 8.5 meters per second. So how long does it take you to stop? Well, we can either say that the area under the graph is 0.35 meters because that's given up here, and we can work out the sums. What shall I do? So I'm going to do this in 2 parts. So let's try this one to start with. We can say that 0.35 equals a half times 8.5 times the base, which is t. So multiply that by 2, 0.7 over 0.85 gives us a total of 0.82. Or we could say to ourselves that actually what we're looking for is the average speed multiplied by the time, which gives us the same area underneath. We could say, let's just leave that little bubble there, could say that the distance covered is the average speed multiplied by the time. And the average speed is the final speed plus the initial speed divided by 2 multiplied by the time period. Of course, we know that that's 0, so really what we're saying is 2s divided by the final velocity. Sorry, we know that that's 0, final. Initial velocity gives us the time, which is 2 by 0.35 divided by 8.5 gives us 0.082. 0.082. What have I done wrong there? Let me just double check on that number. Let's look at the mark scheme. UB2, we are looking at Yeah, 0.08. So that's two lots of... Sorry, 0.082. 0.082. Careful there again, we're going to talk about what's allowed and what's not allowed. 0.08 is allowed, but 0.080 would not be allowed. Because of course that implies that it's to that number of significant figures, but if you include that number then you ought to have the 2 in there. Two ways of doing it, for example. Okay, what's horizontal force? Well, force is mass times acceleration. That's mass times the change in velocity over the change in time. 75 by 8.5 minus 0, because that's what it changes from and to, divided by our time period, 0.082, and that gives us 7741 or 7700 newtons, to the appropriate number of significant figures. Fairly straightforward mechanics on that one. Again, if you'd taken the time just to learn the formula, we've probably got you through that one. Okay, not so easy on this one. Well, it could be. What are we looking at here? Springs, Hooke's law. So explain the shape of the graph, section A to B. Compression against force. It's a straight line through the origin. So in other words, it's directly proportional. But let's not be lazy. Let's say compression is directly proportional to force. Or even you could say it obeys Hooke's law. Why is CD horizontal? Well, this is compressed, and when it hits the base, you can't compress it anymore. So it hits the ground, can't be compressed. Straightforward enough. Okay, what about showing the stiffness of the spring is 1,200? Well, okay, there's a few ways that you can do this. We can either just take a value, because we know that force is equal to K delta L. I think that's the terminology they use in the book, so therefore if you know K is the spring constant, you take the force over delta L, and you can work it out. Or indeed, that's way 1, or indeed way 2 is to work out the compression to delta L, that's your force. The gradient is 1 over the spring constant. So either way, however, they are looking for half a square accuracy. Half a square. Which is not that easy when you read this graph out here. So, for instance, if I was going for a point which I think there, that looks pretty much 0.5, but it's actually not, because if I come up to this point here, I'd say that's about 0.95 to 10, which is different from 5 to 1. So the further away you can go, the better off you probably are in assuming what the real values are. So I'm going to go for about, I'm going to take that one, so K is going to equal F over delta L, which is, I'm over 10 over 0.95, giving me 10.5. And lastly here, of course, what I failed to see there, that is in centimeters. So I need to convert that to meters, which actually gives me 1050 newtons. Correct. We could do it by gradient if you wanted. That's another way in which it can be done. Let's move on. What about suction cup leaves the base, compression spring is, calculate energy stored. Okay, energy stored. So in a delta L compression against force, the energy stored is the area under the graph. And of course, some might say, oh, well, it is as well a half kx squared, which is the same as a half Fx is the elastic potential energy, which of course it is. But if I did throw that number in, a half by the force, so let's just take a look at the force at 0.018, so 0.018 meters, which gives me 1.8 centimeters. If I look at 1.678, that takes me across to this point here, which I think is about halfway in between. It's about 16, 17, 18, 19, 19.25 newtons. So I'd say that's, so that'd be half by 0.018 by 19.25. That should give me, I'm just typing into the calculator, 0.173 joules, or indeed, which is in fact the area under the graph, a half Fx, which is the same thing as the area. So 0.173 joules, or indeed 0.17 joules, effective number of significant figures that I've been given. Okay, what's the maximum possible height the toy can reach? Okay, well, we're assuming that the elastic potential energy here turns into gravitational potential energy. So therefore the figure that I have is going to equal 0.17 mgh. H is going to be 0.17 over mg, which gives me 0.17 over the mass that I've been given, 7.3 times 10 to the minus 3 times 9.81, and that gives me 2.38 or 2.4 meters. Important there, right number of significant figures. What assumptions did you make? There's many here. So the elastic potential energy completely turns into kinetic energy as it bounces off the floor, or indeed that the GPE completely, the kinetic energy completely turns to GPE because there is no air resistance. That's another good assumption. Good, straightforward. Okay, here's a bit of how science works type of question. Explain the advantage of using a video camera over just using the observations. What can we say here? Okay, so you're eliminating the reaction times of humans. So that improves reliability. And precision. What does reliability mean? That's about the repeatability. Are they all similar? Are they repeatable? That will improve upon that, because as it goes up to its maximum height, you can stop it there precisely rather than waiting on reaction times for a human. And also the precision, of course, that's the smallest value you can read, but also accuracy, I would say, which is close to true value. Good. Okay, what do we have here? Why is the student justified 0.5? Well, look at this repeatability I just talked about. Yes, yes, no, that looks wrong. Yes, yes. So the anomaly of 0.65 is taken out. Average of remaining equals 0.45. Good, good, good. Right, about halfway through. Let me just reload the rest of the paper. Okay, here we go. Here is the 6 marker. There will always be one of these in the paper, and we need to find some strategy to deal with this. I would say the best way to deal with it is to treat it like a proper experiment, something which we've done from year 9 upwards, and say to yourself that what do we need to do? We need to work out the independent variable and the dependent variable, and what you're keeping constant or measuring. How you're going to do that, the range of your values, some to keep the readings accurate, and what you're going to plot using data. And if we think about all of those, then we're bound to pick up on the marks which are necessary. Okay then, of course we're describing how you could accurately determine the Young's modulus. Good. So, with the independent variable, what are you going to have to measure for the Young's modulus? Right. You're going to have to measure, you're going to have to change the force, which in turn changes the stress. The dependent, you're going to measure the extension, which in turn measures the strain. How are you going to measure the stress? Well, you need to measure the area with that as well, and you need, with that, a micrometer. How are you going to measure the strain? You need something very precise to work out the extension, like a travelling microscope. What are you going to keep constant? Of course, hopefully the area. So you're going to look for, there's 2 things here, and you're going to measure that, which we've talked about with the micrometer. So we've done that bit. You need to take in more than one place. In order to make sure that the area is not changing. The force, how are you going to get hold of the force? Well, it's the mass of the objects times g. What about the range? We want at least 7 loads. What else will we need? We need, let's think, how do you keep it accurate? Well, we've talked about the micrometer, we've talked about the area and making sure we take it more than one place. Using the data, we can plot the strain against the stress, and Young's modulus will be 1 over the gradient. And some sort of way to draw the diagram would be to show this part held on a bench. You are going to measure somehow the length with a extension travelling microscope stroke ruler to work out the extension over the length, and then you want to put in masses, and the masses will create the weights necessary to stretch this system. Okay, so that's how I would build it about, and just make sure you go through those nice stages there. Let me describe how they actually mark this one, because this is it's always a bit tricky when they mark this. They're trying to make it easy for the examiner to mark. And therefore, what they required was the following. You obviously can get 5 to 6, 3 to 4, or 2 to 1, and usually the differentiation between those comes about from your how clearly it's written. That's how they differentiate between the 2 of those. But what they were looking for here, they were looking for, in order to access the high level, you needed 5 comments from one level and 2 from the other one. And from the 5 you wanted things like, you measure the diameter of the wire, diameter being essential though. So you need 5 of one of these statements. The next one was micrometer. The next one was range of masses. The next one was original length. The next one was ruler for length to use to and the other one was W is mg. So 1, 2, 3, 4, 5, 6 they've given you there, and obviously a diagram. So if you've got 5 of those, you entered into the 5, 6, but you also needed as well 2 from any of the following. Diameter in 2 plus places, 2 or more places. You needed 7 loads. You needed to repeat. That's something I forgot to mention in the first bit. And you needed a microscope. And monitor diameter. Okay, so those 2 of them got you there. Any 4 comments from either of these got you into the 3, 4. And in order to get 2, you needed to get 3 of the comments. In order to get 1, you needed to get 2 comments. Whereas the 5, 6, you needed 5 and 2 of them. So, yeah, I hope that makes some more sense on how we tackle this. This is a very tricky question to tackle, but definitely tackle this. Build it up slowly. How would you do it? How have you seen experiments done in the past? Therefore, what have you done? And this criteria will keep changing each year it's done, but that gives you an idea of how it's tackled. Okay then, right, evidence state from, so if it fractures quickly, it's brittle, because it says A has a higher Young's modulus, so it's stiffer as well. So it's high Young's modulus than B, and it fractures, no permanent deformation takes place. So brittle means there's no plastic region, so A has no plastic region, but it's stiffer. B has a large plastic region, but is less stiff. How would you draw that? Well, what you're looking for is you're looking for stress-strain graphs. I always write the stress here because it's what you change often. You apply it, it's your independent variable. That could be in newtons per meter or, indeed, pascals. Whereas your strain is in, it has no units, it's unitless, remember it's a ratio. Because stress-strain is written this way up, the gradient is equal to 1 over Young's modulus. So therefore A, which is stiffer, is shallower, and also it snaps. B is less shallow, and also it undergoes a plastic region. This is B. So 1 mark, 1 mark. Oh, and the axes are marked. Okay, now we're into some serious number crunching. It says calculate the stress on the wire, and you have been given the strain, Young's modulus, and an original length, but let's just hold that. You want to work out the stress. I know stress over strain is Young's modulus E, so therefore the stress is E times strain, which is 2.80 times 10 to the 11 by 0.24. Now, because that's percent and it looks like a ratio, we forget, but you've got to divide it by 100 to make it into, take it out of the percentage. And only when you do that does it come out as 6.27 times 10 to the 8 pascals, or indeed 6.7. Those are the significant number of significant figures. Remember the trick there, there's 1 mark there. It's 1 for appreciating that and 1 for the answer. The same extension, what load must be applied? Okay, so stress is the force over the area, which is the load. and that equals E times strain. Okay, so let's just go for, so now the force is going to be E times strain times the area, which is the same as E times the strain times pi diameter over 2 squared, which is in fact, remember this is a ratio, you've got to take it out of percentage, and then we go for pi by 1.4 millimeters over 2, square that up, and that should give you 1034 newtons, of which they accept 1000 newtons. Good, significant figures of 2 only here. If you get that bit wrong, then you get 0 marks. If you, sorry, not wrong, but if you try and use the diameter directly in there, or the radius directly without changing to area, you get 0 marks. Okay, a little bit more rearranging there, but not impossible. Okay, what's happening with polarization and unpolarized? Okay, so let's go straight into this. 3 marks. Okay, unpolarized equals oscillations in many planes. What does polarized mean? There's an oscillation in one plane. In other words, if this is the back of a wave we're looking at, it's travelling in that direction. Unpolarized means it's in loads of planes, whereas if something's polarized, it means it's only in one plane. However, we need to mention here that the oscillations are perpendicular to the motion. They're perpendicular to the motion. 1, 2, 3. Because if they weren't and they were longitudinal, then it wouldn't be polarized, so you need to state that explicitly. Okay, a bit of a strange image there, not the best at photocopying. But what's happening here? Well, this object in front looks like a piece of quartz. It gives you 2 images, of which there are 2 images because each one has been polarized slightly differently. So I think that's the first point. The images have light in different planes, and as you rotate the sheet, or the, what do we call, polarizing filter, polarizing filter. Images change intensity. Let's try at 90 degrees. First of all, you see them. Then at 180 degrees, the first image only is seen. Then we get to 270 degrees as you continue to go around, and only other image is seen. And between angles, both are seen, but not full intensity. So if you imagine you've only seen one image, then you move the 90 degrees from that point. Then what happens? I would draw a diagram. I don't think I'd do it justice. It would be a bit of a mess. However, the point being that if one image is held in one plane, the other image is held in another plane, as you rotate through that angle, you will go from not being seen to being seen to not being seen to being seen. A little bit tricky, that one. A lot of words for that one as well. You must make sure they're in the right order and using the correct terms. Okay, explain how a stationary wave is formed. I often confuse this because I often think this is stationary, it's standing still, but it's not. These are both progressive waves. One of them's moving that way, the other one's moving that way, and as they move through each other, they have, so they're moving in opposite directions. They have the same frequency, or if you prefer the wavelength. So therefore, as they move through each other, they superimpose. And we should probably say amplitude as well here. So as they move through each other, they superimpose. And as they superimpose, they then create that form. They create this standing waveform. Good, 3 marks there. 1, 2, 3 marks. So therefore, next question asks then, that's a pretty standard explanation for a stationary wave question. So, next question says, it has a frequency of, has a wavelength of calculated speed. You need to know that that position from there to there is only half a full wavelength. So if that's half a full wavelength, our full wavelength will be twice the length of AP, which is 2.4 meters. So the velocity, which you know is frequency times wavelength, which is a year 9 equation that we learn, is going to be 150 times 2.4, giving us 360 meters per second. Mark. So straightforward, so long as you understood that this is only half a wavelength. Okay, now we're moving to something which is 3 times the frequency as it was prior. So that suggests that for the same wave speed, the frequency is 3 times, then the wavelength is a third. So you need to draw this, as I've done very badly, with a third of the wave, so you're getting 3 times the number of waves than you did before. 2 marks. Making sure that this is, I suppose 1 mark's given there for the shape, and 1 that they're quite regularly sized. Okay, nearly there. Ultrasound. Explain what is meant by the frequency of a wave. Very simple. I'd go for number of cycles or oscillations per second. You could then talk about the number of waves divided by the time period, or 1 over the time period, but I'd go for that one to start with. What is a longitudinal wave? This one caught me out, I think, when I first read it. It's a vibration of a medium, and that's the important point, because it doesn't happen in a vacuum, it only happens in material. So it's a vibration of a material which vibrates in the same direction as it travels. Boom, boom. Okay, another, I think this one's quite straightforward as well. It's asking you to deal with the wave equation, frequency. It's asking for you to calculate the frequency of this ultrasonic thing, bearing in mind it's in millimeters. So we get 1540 over 0.5 times 10 to the minus 3, equaling 3.08 times 10 to the 6 meters per second is the frequency. So hertz as the frequency. Of course, 3 there, 2 there, that's actually 2 significant figures, so your answer should be 3.1 times 10 to the 6 in terms of hertz. Last one. Okay, this is, I don't know whether you've seen this experiment, it's called Kunstube. I think I've spelled that right, real danger in pronouncing that. And what happens is a standing wave is set up because you have a wave coming in, reflecting, and coming back out again. We are pretty much in this territory here, but it's done with a longitudinal wave. Okay, what happens here? Well, the mark scheme gives loads and loads of examples of what's happening. However, what you need to describe is describe and explain the effects the waves have on the particles. Okay, you will get a series of nodes and antinodes. And at the nodes, that means the particles are at maximum displacement, i.e. they're moving lots, and the nodes, they're stationary. In actual fact, you just get this collection of particles at different points. Their amplitude changes. And this one is, the amplitude is less, and this one, the amplitude is great. And on either side of your nodes, vibrations are in antiphase. So anything happening that way, it's happening that way, and if it's vibrating that way, it's coming in that way. If that is a node, I should have written an N there probably. Okay, and why is it created? Well, you have a standing wave because there's a reflection and a superposition which creates nodes stroke antinodes. Okay, a bit tired on that last question, so I wasn't writing out too clearly, but that's essentially, you're only going to need 3 of those very many marks there. Right, that's it. Apologies for the noise.